Welcome to this lecture series on materials informatics applications in battery materials design. In this first chapter, we'll build a solid foundation by understanding how batteries work, the key challenges in battery development, and how AI and machine learning are revolutionizing this field. By the end, you'll appreciate why MI is becoming essential for next-generation battery development. In this chapter, we have four main learning objectives. First, you'll understand battery operating principles at a fundamental level. Second, you'll learn the key performance metrics that define battery quality. Third, we'll explore the major challenges facing battery developers today. And fourth, you'll see how materials informatics provides solutions to these challenges. Let's begin our journey into battery fundamentals. At its core, a battery is a device that converts chemical energy into electrical energy, and vice versa. During discharge, chemical reactions release electrons that flow through an external circuit, powering your device. During charging, we reverse this process by supplying electrical energy to restore the original chemical state. This reversibility is what makes rechargeable batteries so valuable. Let's look at the structure of a lithium-ion battery, the dominant rechargeable battery technology today. It consists of three main components: the anode, typically made of graphite, which stores lithium between its carbon layers as lithium graphite; the electrolyte, a liquid solution such as lithium hexafluorophosphate dissolved in organic solvents, which carries lithium ions; and the cathode, such as lithium cobalt oxide, which accepts and releases lithium during cycling. During discharge, the anode undergoes an oxidation reaction, releasing lithium ions and electrons. The lithium ions travel through the electrolyte while electrons flow through the external circuit, doing useful work. At the cathode, a reduction reaction occurs where lithium ions and electrons combine with the oxide material. The overall cell voltage is about 3.7 volts. Charging reverses these reactions. Energy density is perhaps the most important battery metric, measured in watt-hours per kilogram. At the electrode material level, it is capacity in milliamp-hours per gram times average voltage, which gives watt-hours per kilogram of active material directly. A complete cell also carries the anode, separator, electrolyte, current collectors, and casing, so cell-level energy density comes out at roughly a third of that figure. Today's lithium-ion cells achieve 200 to 300 watt-hours per kilogram at the cell level. The target for next-generation batteries, like all solid-state, is 500 watt-hours per kilogram, essentially doubling today's performance. Beyond energy density, several other metrics matter. Power density measures how quickly energy can be delivered, critical for applications like EVs needing rapid acceleration. Cycle life counts how many charge-discharge cycles until capacity drops to 80%. Coulombic efficiency measures the ratio of discharge to charge capacity, ideally 100%. C rate indicates charging speed, where 1C means full charge in 1 hour. Now let's explore the different types of batteries being developed. While lithium-ion dominates today's market, several next-generation technologies promise even better performance. Understanding these options helps us appreciate where MI can have the greatest impact. Lithium-ion batteries remain the workhorse of portable electronics and electric vehicles. Various cathode chemistries exist: LCO for phones, NMC and NCA for EVs, and LFP for safety-critical applications. Anodes are typically graphite, though silicon alloys offer higher capacity. LIBs achieve 200 to 300 watt-hours per kilogram and power everything from smartphones to Tesla vehicles. All solid-state batteries replace the liquid electrolyte with a solid material. This offers tremendous advantages: no leakage risk, higher safety, potential for energy densities exceeding 500 watt-hours per kilogram, and operation across a wider temperature range. Solid electrolyte options include sulfides, oxides, and polymers. Major automakers like Toyota are targeting commercialization by 2027. For even higher energy density, researchers are exploring lithium-sulfur and lithium-air batteries. Li-S uses sulfur as the cathode, with a theoretical capacity of about 1,670 mAh per gram, roughly 6 times the theoretical capacity of lithium cobalt oxide. Li-Air theoretically offers an astounding energy density far exceeding current technologies. However, both face significant challenges with cycle life and remain in the research stage. Sodium-ion batteries offer a compelling alternative for cost-sensitive applications. Sodium is abundant in seawater, eliminating supply concerns. These batteries cost about 60 to 70% of lithium-ion equivalents, while energy density is lower at 150 to 200 watt-hours per kilogram. They're ideal for stationary storage and budget EVs. Chinese manufacturers, led by CATL and Hainan Battery, moved sodium-ion cells into commercial production from 2023. Despite decades of progress, battery development still faces significant challenges. The traditional approach of synthesizing materials, testing them, and iterating is painfully slow. From initial research to commercial products typically takes 10 or more years. Let's examine the key challenges that materials informatics can help address. Traditional battery development follows a sequential process. Literature survey takes 1 to 3 months to identify candidate materials. Material synthesis requires 3 to 6 months of lab work. Evaluation testing, including charge-discharge cycling and safety tests, consumes 6 to 12 months. Finally, optimization of composition and processing takes another 12 to 24 months. Total development time, 3 to 5 years minimum. Improving energy density remains the primary goal. Current lithium-ion batteries need to roughly double their energy density to satisfy EV range demands. This requires high-capacity cathodes and potentially lithium metal anodes. Achieving this safely is one of the field's greatest challenges. Charging time is a major barrier to EV adoption. Current batteries need 30 to 60 minutes to reach 80% charge. The target is 10 minutes, which would match gasoline refueling convenience. But fast charging causes problems. Lithium plating on the anode risks internal shorts, heat generation accelerates degradation, and ion diffusion simply can't keep up at very high currents. Battery cycle life must improve dramatically. Current batteries last several hundred to over 1,000 cycles before reaching 80% capacity retention. The target is several thousand cycles, equivalent to hundreds of thousands of kilometers for an EV. Degradation mechanisms include layer growth consuming lithium, structural collapse of cathode materials, and lithium plating during fast charging. Safety concerns remain critical, especially for large battery packs. Thermal runaway is the primary risk. An internal short causes heating, which triggers electrolyte decomposition, more heat, and potentially fire or explosion. Solutions include solid electrolytes that don't burn, flame-retardant additives, and sophisticated protection circuits. Zero accidents is the only acceptable target. Cost reduction is essential for widespread adoption. Battery packs currently cost around $150 per kilowatt-hour. The target is $50 per kilowatt-hour, at which point EVs become cost-competitive with gasoline vehicles. Major cost drivers include cobalt and lithium, both subject to price volatility and supply chain risks. This is where materials informatics transforms the game. By applying machine learning, optimization algorithms, and massive datasets, we can dramatically accelerate battery development. Let's see how MI addresses each of the challenges we just discussed. Traditional DFT calculations take days to weeks per material. Machine learning models predict capacity and voltage in seconds. Using random forest, XGBoost, or graph neural networks trained on over 100,000 materials from the Materials Project, we can screen tens of thousands of candidate materials per day. These models achieve high prediction accuracy, enabling rapid identification of promising candidates. Instead of running 6-month cycle tests, LSTM and GRU neural networks can predict long-term degradation from just the first 100 cycles. Remaining useful life prediction achieves high accuracy. This reduces testing time dramatically and enables early detection of defective cells. A joint team from MIT, Stanford, and the Toyota Research Institute demonstrated this approach in a landmark paper published in Nature Energy in 2019. Bayesian optimization with active learning revolutionizes material discovery. Instead of random experiments, we intelligently select the next material to test based on predicted performance and uncertainty. This reduces required experiments significantly. A frequently cited example is the optimization of sodium-vanadium fluorophosphate cathodes for sodium-ion batteries, a known material family whose composition was refined this way rather than discovered from scratch. Development timelines shrink from about 5 years to about 2 years. Reinforcement learning optimizes charging protocols by learning the best current profile to minimize degradation while maximizing speed. The AI observes state of charge, temperature, and internal resistance, then decides charging current. Stanford researchers achieved rapid charging with minimal degradation. This work was published in Nature in 2020 and has been widely influential in industrial fast charging development, although the protocols that individual automakers actually ship are not public. Battery development isn't just an academic exercise. It's driving a massive global industry transformation. Let's look at the market size, key players, and environmental impact of this technology revolution. The global battery market was worth $50 billion in 2024 and is projected to reach over $100 billion by 2030, growing at 15% annually. Electric vehicles drive about 70% of demand, followed by stationary energy storage at about 20% for grid applications, and consumer electronics and IoT devices making up the remainder. This represents one of the fastest-growing technology sectors globally. The market is led by CATL of China with about 1/3 of the market share, followed by LG Energy Solution, BYD, Panasonic, and Samsung SDI. These companies are investing billions in new factories, and R&D major automakers like Tesla and Toyota are also developing in-house battery capabilities to secure supply and accelerate innovation. Batteries are essential for achieving carbon neutrality. EV adoption alone could reduce CO2 emissions by hundreds of millions of tons annually by 2030. Stabilizing renewable energy with grid storage adds even more reduction potential. The circular economy goal targets high lithium recovery rates through recycling and repurposing retired EV batteries for less demanding stationary storage applications. Let's summarize what we've learned. We covered battery fundamentals, operating principles, key metrics, and battery types from lithium-ion to sodium-ion. We examined 5 major challenges: energy density, fast charging, cycle life, safety, and cost. We saw how MI provides solutions: rapid prediction, degradation forecasting, efficient discovery, and protocol optimization. And we appreciated the industry's enormous scale and environmental importance. In Chapter 2, we'll dive deep into MI methods specialized for battery materials. You'll learn about the 4 types of battery descriptors: structural, electronic, chemical, and electrochemical. We'll explore prediction models including random forest, XGBoost, and graph neural networks. We'll cover cycle degradation prediction using LSTM networks and material search through Bayesian optimization. See you in the next chapter.